Welcome to Study Loop.
For problem A, we need to find the radius of the Earth and the mass of the Earth in order to calculate the density of the Earth. I've looked these up in the text. They are as follows. Radius of the Earth, which we denote as r sub e, is 6.38 times 10 to the 6th meters. The mass of the Earth, m sub e, is 5.98 times 10 to the 24th kilograms. Using these values, we can calculate the density of the Earth using the following formula for mass density: mass over volume. And we know that the Earth is almost spherical, so we can use the formula for a sphere in the denominator here. Plugging in those numbers, you'll find that the Earth has a mass density of 5.5 times 10 to the 3rd kilograms per cubic meter. We also can work out the density of atomic nuclei. We'll use equation 30-1 again, as we did in earlier problems. And we'll divide that by the expression for a spherical volume. We'll approximate the atomic nuclei that way. The mass of atomic nuclei can be written as 1.06605 times 10 to the negative 27th kilograms times the atomic mass number of the element in question, which we're going to call here A. We're talking about uranium-238. We would put a 238 here, but it turns out once we calculate the bottom using that same R spherical volume here, that A will cancel. So we have 1.2 times 10 to the negative 15th meters. And this is multiplied by the atomic mass number cube rooted. But again, this whole quantity is a radius, and we're going to cube that. So the cube of a cube root is effectively a to the first. We have a to the first on top, so those cancel. So the moral of the story here is that the density of atomic nuclei doesn't depend so much on the type of nucleus it is. They're all roughly the same density, regardless of the element we're talking about. So plug in the numbers in here. We find that this works out to a density of 2.30 times 10 to the negative 17th. I'm sorry, not to the negative, 10 to the positive 17th here. and that is in units of kilograms per cubic meter. Given both these densities, we can now determine that the radius of the Earth, given it has this density of 2.30 times 10 to the 17th kilograms per meter, what its radius would it be in that case? So in order to find that out, we can work out the formula here for this new r. It's the radius of the Earth if the Earth were to have the density of atomic nuclei. Which is going to be this mass of the Earth that we have above, but instead of using the density now of the Earth, we're going to use the density of the atomic nuclei that we just calculated there. And in addition, because we're solving this r from the expression of a sphere, in this side we're going to have the inverse of the spherical geometry constant there. This is a cube root. Plugging this in, we find this works out to 183.8 meters. So you can see that this is orders of magnitude smaller than the radius of our actual Earth of 6.38 times 10 to the 6 meters. It's actually around 3 orders of magnitude smaller. So nuclei, atomic nuclei, are way, way more dense than ordinary matter. Now, on to problem B. We're looking for the scale factor, going sort of the opposite direction here. What the radius of uranium-238 would be if that uranium-238 nucleus had the density of the Earth now. So this actually is a little bit easier to solve, and there's less constants to look up. But what we're effectively looking to solve is a proportion. I'm going to express it this way, that we're looking for this modified radius. This is the radius that results with a different density as compared to the original radius. That's going to change, or I mean, this proportion is going to be a constant factor that we're going to call A here. I'm just going to call that a scale factor. That is what we're after. So we know a few simple things that we can use to make this problem go quicker. The first being that this ratio, R modified compared to R original, is proportional to the cube root of the corresponding volume modified to volume original by the fact of the spherical volume equation. And we can express each of these volumes as the mass of the uranium nucleus, which is the same for both modified and original versions. These can each be divided by densities, but for the modified case, that's going to be the Earth's density. The original case is the density of atomic nuclei. these m's cancel. Now this expression can be written as the original density over the modified density. So let's plug in some numbers here. Oops. We find that, I'll just write them out so it's clear. You can check for yourself. The original density of the uranium 238 nucleus is 10 times, or I'm sorry, 2.3 times 10 to the 17th. The density of the Earth, we calculated above, is 5.5 times 10 to the third. And I'm sorry, this is in units of kilograms, meters per kilograms per cubic meter. This was 5.5 times 10 to the third kilograms per cubic meter. If you crunch those numbers, you'll find that this is equal to 3.5. Ugh. Oh my. This is equal to 3.5 times 10 to the fourth. So the modified radius, if a uranium nucleus was to have the density of the Earth, its radius would be 35,000 times larger than it is having the normal density of atomic nuclei. We'll box that answer. And this answer also needs to be boxed. That concludes our problem.